Now we're going to look at z-scores. A z-score tells us the number of standard deviations that a data value is from the mean. This is a type of standardized score. Now, one of the ways that a standardized score, like a z-score, is useful is to compare unlike quantities. So let's say in this rather far-fetched example that there's a decathlon, and a decathlon is when athletes compete in 10 different events for an overall score. Some scores higher in one event and others in another. So how can an overall score be computed that compares, for example, the best long jump with the best shot put throw, or the best 100-meter dash with the best high jump? In this rather far-fetched example, let's say that the top 3 competitors ended the first 7 events with a tied score. We want to use the results of the last 3 events to determine the winner. So what we have here are our 3 competitors: Howard Huge, whose specialty is the shot put, Sam Speedy, whose specialty is the 100-meter dash, and Johnny Jumper, whose specialty is the long jump. But they are also good in the other events, just not as good as each other. Now, the mean and standard deviation listed here are not the mean and standard deviation of just these 3 values. This is the mean and standard deviation of all of the competitors in that event. So what we want to see is how much better or worse in terms of number of standard deviations to the mean are each of our competitors. So the mean for the 100-meter dash is 10 seconds. Obviously, the less time you take in the 100-meter dash, the better. So we're going to award positive scores to people who score less than 10 seconds and negative scores to people who score more. So it's a little bit different than what we would normally see on a real distribution of data. The mean is 10 and the standard deviation is 0.2. So we see that Howard Hughes is 1/2 of a standard deviation slower than the mean. So we're going to award him a -1/2 for 1/2 of a standard deviation slower. Sam Speedy is 1/2 of a standard deviation faster, so we're going to award him a +1/2. And at 10.3 seconds, Johnny Jumper is 1.5 standard deviations slower than the mean. Now in shot put, the mean was 60 and the standard deviation was 3 feet. So Howard Huge has a +2 standard deviations above the mean in his shot put. Sam Speedy is right at the mean with 0, and 63 is +1 standard deviation. So they all did at least as well or better than average in the shot put. In the long jump, our standard deviation is 6 inches, or 1/2 of a foot, 26 feet. So here Howard Huge is right at 0 in the standard deviations. Sam Speedy is 1 foot over, which would be 2 standard deviations better. And he's 2 standard deviations plus 3 inches, so that would actually be 2.5 standard deviations better. So now if we add up the total scores in terms of how much better or worse they are than average in each of their events, Howard Huge's total score would be -1/2 plus 2 plus 0, or a total of 1.5. Sam Speedy's 1/2 plus 0 plus 2, or a score of 2.5. And Johnny Jumper, -1.5 plus 1 plus 2.5, for a total z-score of 2. So we see here we have our gold medal winner, our silver, and our bronze. So takeaway from this is using z-scores or standardized scores is a good way to compare unlike quantities. Now, how does that work with more interesting numbers, shall we say? Well, I've many years done projects where I've collected students' heights, and so here's a kind of a compilation of many of the heights, mostly juniors and seniors, that I've collected over the years, and I calculated the mean and standard deviation for male and female heights in inches. So how do we calculate a z-score? The z-score is defined as the data value minus the mean over the standard deviation. So the data value minus the mean tells you how far the data value is from the mean. And then when you divide it by the standard deviation, that would tell you how many standard deviations in a way from the mean that value is. So I want you to find the z-score for your height. I'm going to do mine. You might remember that 5 feet is equal to 60 inches and 6 feet is equal to 72 inches. So if off the top of your head you're not sure how many inches you are, that would help. I'm 5'9", so I'm 69 inches tall. So my z-score would look like this. 69 minus the mean for the female, 65.3, divided by 2.9. So I'm going to pause a minute and calculate. My z-score is 1.27. How would I interpret that? Do z-scores have units, for example? So let's just think about this. What I did was 69 inches minus 65.3 inches divided by 2.9 inches. Because remember, 2.9 is, the standard deviation is the typical amount of variation from the mean, so that would still be in inches. If I do 69 minus 65.3, that would be 3.7 inches divided by 2.9 inches. No, there aren't any units. So z-scores don't have units. They are just known as standard deviations. So what does the sign tell you? Okay, so if we have a positive standard deviation, it means I'm above the mean. Because notice my number here, 69, is bigger than the mean. If you take a number that's smaller than the mean and subtract the mean, you're going to get a negative standardized score, or a negative z-score. So this means negative means below the mean. So I would interpret my value as my height is 1.27 standard deviations above the mean for female heights. So I'm taller than average. If you had a negative z-score, it means you are shorter than average. And the larger the standard deviation, the farther away from average you are, either in the positive or negative direction. Because the mean would have a z-score of what? If we took the mean height, 65, so if someone happened to be exactly 65.3 inches, 65.3 minus 65.3 divided by 2.9, and this is for the females, notice that ends up to be 0. And that's going to always be true. The mean of a distribution has a z-score of 0. Also, just for your information, a data value that is more than plus or minus 2 standard deviations from the mean is considered unusually high or low. And a data value that is more than 3 standard deviations from the mean is very rare. So if you have a height that is more than 2 standard deviations above or below the mean, it means you're very unusual. You fall in a small group.